consisted of these two overall efficiency. So internal quantum efficiency actually we'll see it that is related to since semiconductors, electron hole pairs will be considered. In fact, if you see LED, light is emitted because of recombination of charge carriers. So when the carriers are recombined, then only light is emitted. So in that case, that recombination is related to internal quantum efficiency, and external quantum efficiency is related to how many photons actually emitted in a particular directions and forward directions. So that is external quantum efficiency. We'll see the details of it. So overall efficiency should be high. And next is it must have longer lifetimes, right? Generally LEDs are used, but sometimes laser sources are also used. But laser sources, the lifetime is reduced because of high temperature effect will be there. But that can also be minimized to get longer life. Generally, it should last 10⁶ to 10⁸ hours of this range, lifetimes. Digital modulations, fourth one. What is that? See, if a fiber is placed here, a source, you have seen the basic elements, sources are there, input signal, next drive circuit, next sources, next fiber, right? So input signal is here. So actually sources, the sources are being modulated by the modulating signals, right? So, I'm giving the examples. I'm talking the voice, speech signals. The speech signals, if you want to transmit it, that will be modulated. That will modulate the high frequency optical signals, right? So basically in the optical fiber, the signal that is propagating, it is actually modulated optical signals, modulated optical signals, right? Modulated signal will be propagating through the optical fibers. So once you use the terms modulatings, then that means certain kinds of modulations are there. You know the conventional modulation schemes are there, amplitude modulation, frequency modulations, phase modulation, etc., right? Not all those type of modulations are used in fiber optic systems. We'll see a specific type of modulation schemes are used. Intensity modulation is used in this case, because here in light, you see it's a very high frequency, 10⁻14 to 10⁻15 hertz. So amplitude modulation, it is not being used here. Actually, in this case, intensity is considered. So intensity modulation is used. Of course, some other digital modulation schemes are also there, like ASK, ASK, those modulation schemes are also there. We'll see it. So the sources should be considered like that. We can have a particular modulation schemes. We can implement the modulation schemes on that particular source. So that is the digital modulations. They must satisfy that conditions. I mean, we can modulate the source with a specific modulation format. That is the fourth conditions. The fifth condition is also most important, compatibility. I have mentioned just now. If you have a big source, if you have, that cannot be used for fiber systems, because fiber dimension is very thin. Very less number of photons will be launched within the fiber. So output power almost nil will be there. So compatibility is important. Means fiber dimension, the source dimensions, they must be of the similar similar dimensions. Right. So compatibility is another aspect, requirement for optical sources. So these are the important requirements for sources that can be used for fiber optic communication systems, right? And if you see these sources, they can be either incoherent sources. These sources, you can classify the sources in two types, either the incoherent sources or can be coherent sources. Generally, all natural sources, not generally, it is all natural sources are the incoherent sources. What about the source you see, that is the incoherent sources? But the laser sources, which are the artificial sources can be coherent sources, right? They're just like lasers, right? And if you see incoherent sources, all incoherent sources are not suitable for fiber optic systems, right? Say tungsten lamp, fluorescent tube, the dimension is quite large, right? So you have sources that must be compatible with the fiber dimensions. So generally, light emitting diode, which is very small in size. So that is used, and also we can easily modulate their optical beam. That's why LEDs are widely used nowadays for fiber optic communication systems. Of course, very long distance systems, laser sources are used. Say undersea cable systems from one continent to another continent. That is also based on semiconductors, but that is semiconductor lasers. That is called ILD, injection laser diode, or semiconductor lasers. Right. So among the incoherent sources, we'll focus on the LEDs, which are widely used, light emitting diode. First, we'll light emitting. Next, we'll consider these sources, other sources. I mean, laser sources. So this is one type of source, incoherent source. Another type of source is that is the coherent source. Maybe I have mentioned earlier, coherent sources means any source can be considered a number of point sources. Suppose any source is here, it can be considered a number of point sources, consisting of a number of point sources. It has some finite size, so that means that source can be considered a number of point sources. And if these point sources they are not related, there is no correlation among themselves, then this is called the incoherent sources. But if sources are correlated, I mean, if there exists a definite phase relations among themselves, right, then that source is called the coherent sources. A definite phase difference would be maintained among the point sources. If that is the case, then it is called the coherent sources. Right. Of course, these coherent sources. Okay, just before that, let's see more about coherent sources. We'll see it. Before that, you see the lasers. Lasers are the coherent sources. And among the lasers, if you see, there are various type of lasers are there, like solid lasers, like say ND glass, ND YAG, ruby lasers. The most, all the important lasers. Other solid lasers are also there, but the important lasers, gas lasers. Using gas acting mediums, lasing mediums, you can have the gas laser also, like helium neon, argon ion, argon krypton gas lasers are there. Also, the lasing medium can be semiconductors. So accordingly, you can have, just I mentioned, injection laser diode or semiconductor lasers would be there. This times the lasing medium is semiconductors. So semiconductor lasers are there. Also, you can have excimer laser, X-ray lasers, etc. High frequency lasers are there. Excimer lasers, they are based on the inert gases, like say helium, argon, or can be neon, etc. And inert gases, inert gas lasers. Example, X-ray lasers are also there, like this. Many more lasers are there, dye lasers, plenty of lasers are there. Right, but all those lasers generally not suitable for fiber optic systems, because you keep in mind you have to have modulation. Modulated optical beams. So modulation format is required, as well as compatibility is required. So semiconductor lasers here easily can modulate their optical beams, and also the dimension is compatible with the fiber dimensions. So semiconductor lasers are widely used for the fiber optic systems. Of course, I told you, whenever excessive high power is required, that times solid lasers are required. Say, for example, Soliton generations. We'll see in the last models that time high power lasers are used. Also, these lasers are very highly coherent. Semiconductor lasers are not coherent, but not highly coherent. It is a multi-mode lasers, right? We'll see it, different modes are there in lasers. Okay. So, and semiconductor materials can be of different types. We'll see, and also keep in mind, whenever you consider the semiconducting sources, whether it is LED or laser, there also we have to consider the heterojunctions. Generally, PN junctions devices are there, LED, but normal PN homojunctions are not used for LED or fabrication of LED or light emitting diode. They must be of heterojunctions. Heterojunction means, generally, if you say silicon PN junction, silicon diode, silicon PN junction diode. So the material is silicon. It can be P-type, it can be N-type, depending upon the doping. Next, if you arrange together, so you will get the PN junctions, right? But same silicon is here. But here, heterojunctions, P-type can be one type materials, N-type can be another type of materials. So like say gallium arsenide, gallium aluminum arsenide, like these things. But different band gaps of the silicon. Here similar means here same band gap is used for P-type and N-type, but here different band gaps are there. So that's why it is heterojunctions. So we'll see it, details about it. Right. Something more about coherent sources. In coherent sources, you can see it here. Incoherent sources, just I mentioned, the conventional sources are incoherent sources, but we'll focus on LED because you can easily modulate their output beams. That's why it is widely used in power pack systems. And among the coherent sources, just now I've seen it, semiconductor layers are widely used for power pack system. Here also you can easily modulate, but in other layers, you have to use another device to modulate their optical beams. And external modulators are required. Modulators are required, right? For other than semiconductor lasers, right? And keep in mind also, in case of fibers, multimode fibers, fibers, both LED and laser diodes can be used. But for SN fiber, you cannot use LED. LED cannot be used because very less light will be coupled within the SN fibers. That times laser diode only laser sources or laser diode must be used for SN fibers, right? And something about these coherent sources, just now I mentioned there is a definite correlations between the point sources. Then it is the coherent sources. Actually, if you go into details of it, there will be two types of coherence. One is temporal coherence and there is spatial coherence. Temporal coherence is related to the monochromaticity. Monochromaticity. Suppose a particular source is a red. If you have a red beams, then you see it is not a delta functions. Rather, it has spread in wavelength is here. Even a red, so you can expect say 616 nanometer. It's a red wavelength, right? But any source generally does not emit a particular wavelength. Rather, it will emit this wavelength together with some spread. That is delta lambda, right? And if delta lambda is very narrow, then it is called the almost coherent source. I mean, nearly the monochromatic source. Then it is the coherent source. So temporal coherence should be high. That means delta lambda should be very narrow. So again, if you just see the mathematical forms, say y equal to a sin omega t plus minus theta. This is a monochromatic waves. Why? There will be only one frequency is here, omega, right? So that is the monochromatic. But no sources, natural sources, even the laser sources, they are not emitting a single wavelength. They are emitting a wavelength together with some line width, delta lambda or delta nu in terms of frequency, right? So that is the temporal coherence related to monochromaticity of the source. So when you fabricate the coherent source, your aim will be to get it will be such that delta lambda will be very, very narrow. Then it will be highly coherent. Another coherence is here, that is spatial coherence. Spatial coherence means it is related to the divergence. You know, in a laser source, when you see the laser source, you see it goes straight. Even if you can have a reflected beam from several kilometers, even from moon also, you can have a reflected beams. But normal sources, after a certain distance, there will be no trace of it, right? So that is property property it is here in coherent sources because it has very high spatial coherence. Spatial coherence that is related to the distance among that point sources just now mentioned. These ones, the distance would be such that the different phase relation will exist, right? So that is the spatial coherence. Actually, we'll see it. That is possible if you have actually it is multimode device TEM, PL cube, etc. So longitudinal modes, transverse modes are there. The transverse modes actually transverse modes related to the spatial coherence. and longitudinal modes corresponds to temporal coherence. So spatial coherence, which actually related to the beam width, beam profiles, beam divergence. These are related. These are determined by the spatial coherence, right? That is related to the transverse modes. We'll see it. We'll see when we consider the laser sources. This time, these things will be discussed more details. So just for the beginning, you should know all those things. Whenever high temporal coherence, high spatial coherence is here, then you can say it is highly coherent source. And generally, laser sources are high coherent sources, right? Another thing is this: if you consider this a sin omega t plus minus theta, that means it is sinusoidal from minus infinity to plus infinity. So that's why it is monochromatic. But if you have a practical sources, no sources, natural sources are not monochromatic in the sense here the pulses emitted just like this, truncated. You see it here, truncated. It is not sinusoidal from minus infinity, rather within a certain time intervals, it may be sinusoidal, right? But not minus infinity to plus infinity. Truncated sine wave, you will get it. And so that's why the natural sources are not coherent sources. So with this basic concept, now we'll focus on these LED sources. Before going to the details of their configurations or the constructions, you should know their output for LED and laser sources. Just now I mentioned we'll focus on LED, light emitting diode, and laser diode because both are based on semiconducting materials. Semiconducting materials, right? And why you're considering semiconducting materials? That is because you can easily modulate their optical output, right? So here you can see their output. It is actually a large difference is here, though both are p-n junctions. But if you see their output, large difference is here. This is for LEDs. It's a particular temperature, and this is the output for laser diode. You see it here. It is highly nonlinear in case of laser diode. But in case of light emitting diode, almost if you increase the current, you can get the output. Right? Every year you get the, of course, to some extent, nonlinearity is here. Anything is not linear. Linear means it's a perfect sense, right? All natural processes are non-linear, right? So you see it here. This is the LED sources. If you increase the current, output will increase. But in case of laser diode, you see, if you increase the current, initially there will be no output, almost zero output, you'll get it. But a certain output will get it, that is negligible. But after a certain threshold current, threshold current, there will be a dramatic increase in the output. You see it here. And this is the laser output. This is the laser output, and this is the LED output. Right. This output is same for all type of lasers. Though I am showing it here for laser diode, but it is actually true for any type of lasers. Right. After a certain threshold current or threshold pump power, right, this there will be dramatic increase in the output. Of course, here drawback is this here. It is much more temperature dependent compared to LED. If T2 another temperature is there, its output will be deviated. But here large deviation will be there, and the same temperature difference is here for the case of laser diode, right? So laser diode generally, not only laser diode, for all type of lasers, generally a cooling arrangement is made. That cooling system can be either air cooling, can be gas cooling, or can be water cooling, like these things, right? Otherwise, lighting will be limited. So these things are there, and here you can see this is because you see the highly nonlinear, that is because lasers, it is light amplification by stimulated emission of radiations. So that stimulated emission means actually there are two types of emissions: spontaneous emission, stimulated emissions. In case of lasers, for any sources, these type of emissions should be there. But in case of laser sources, the stimulated emission dominates. That's why you're getting this type of nonlinearity, right? We'll discuss in details when we discuss the laser sources. Probably to some extent you have read it earlier also in your school levels. Laser sources, right? So with this basic concept, now let us consider the other aspects. here you see, just now I mentioned, they are based on semiconductor materials. Now, what type of semiconductor materials that can be used for fabrication of LED or laser diode, right? Generally, semiconductor materials, if you consider, they can be either indirect bandgap materials or can be direct bandgap materials, right? Uh, in case of indirect bandgap type materials, so for example, silicon, germanium, these are actually indirect bandgap types. In that case, the conduction band, valence band, conduction band minimum and valence band maximum, they will not occur at the same momentum value, right? Indirect bandgap types. And in case of direct bandgap types, uh, the conduction band minimum and valence band maximums maximum occur at the same momentum value. Actually, whenever there is a transition, generally you have seen this conduction band, valence band, you are writing this one, forbidden band. But these state lines, these are actually these are only approximations. But original, if you see, their band is like the elliptical in natures, right? Wave functions like these things. So the conduction band minimum and valence band maximum, if they occur at the same momentum value, then it is called the direct bandgap type materials. In fact, whenever there is a transition from conduction band to the valence band, both energy and momentum must be conserved. That is the principles, right? So in this case, direct bandgap type materials, you see, I'm showing it. The diagrams you can see. This is direct bandgap type materials. You can see it here. This is the conduction band, and this is the valence band, right? And this is the band gap. This is the band gap. Conduction band minimum. This is the conduction band, and this is the valence band, right? This is the band gap. And I told you, whenever there is a transitions from conduction band to valence band, it's a high energy, low energy. So energy will be emitted, energy will be in terms of photons. So h nu, right? So in this case, h nu equal to photon. It is this Eg equal to E direct, right? That is the photon energy, right? Is nu direct. So this is direct bandgap type materials. But in case of indirect bandgap type materials, you see, this is the conduction band minimum and valence band maximum. They occur at different momentum value. This is the momentum, this one momentum value. So if that is the case, then if there is a transitions, you see it will be against the principle of conservations. So in this case, to get the transitions from valence band to the conduction band to the valence band, a third particle must participate in the process. Third particle, like say phonon, crystal lattice vibration, etc. Phonon, nothing but a crystal lattice vibrations, just like photon, right? The third particle must participate in the process to conserve the momentums. Right. This is energy, and this is x-axis, the momentums. So to conserve the energy and momentums, a third particle must participate in the process. So in that case, it can be if this is the E direct, and this is the you see, this is a phonon energy of phonon. Then so from here to here, it will be E indirect plus E phonon. E indirect plus E phonon, whenever there is a transitions, right? But it can also be less than this E indirect. So it can be E indirect minus E phonon. If you consider this point, then it is the photon energy H nu. So in this case, a third particle must participate in the process to conserve momentums. That's why here band-to-band transition is not the most probable case, whereas in case of direct bandgap type materials, band-to-band transitions are the most probable cases. So that's why your aim will be to consider the materials that will have direct bandgap type configurations. Unfortunately, silicon, germanium, all these developed technologies, these, the single element semiconductors, they are indirect band gap types, right? So these are generally not used for LED sources. So you, for LED sources or laser diode sources, you need direct band gap type materials, and for which conduction band minimum, valence band maximum will be at the same momentum value, right? Now the question is, what are the direct band gap materials? They are like 3,5 compound semiconductors, like say gallium arsenide, uh, gallium arsenide, or gallium arsenide phosphide, like these things, right? 3,5 compound semiconductors. Right. One example is this gallium arsenide, gallium aluminum, gallium arsenic phosphide, gallium aluminum arsenide, gallium aluminum arsenide, GALAS, like these things, right? These are actually direct band gap type semiconductor materials. For example, if you consider gallium arsenide phosphide 1 minus x the mole fractions, then if x is less than equal to 0.45, then it is dull band gap types. But of course, if x greater than this one, then it will be direct band gap types, right? So generally, it must be a 3,5 compound semiconductors, and in this case, these combinations can be binary, can be ternary, can be quaternary, like these things, right? It can be indium gallium arsenide phosphide also, indium gallium arsenic phosphide. It can be like these things. Here it is 1 minus x, x. Here it is 1 minus x, x, y, 1 minus y, like these things. Right. And in this case, the band gap can be varied by changing the value of x. And you see here, what will be the emission wavelength for such cases? See, it can be calculated like these things, equal to h nu, hc by lambda. So lambda, the emission wavelengths. Emission wavelength lambda, it is 1.24 upon Eg. If you just put the value of Planck's constant c velocity of light, then you can have it, if Eg in electron volt, then 1.24 upon Eg. If you can remember this one, there is no need of solving these ones, 1.24 upon Eg. So in this way, you can calculate the wavelength of light. Now, how to calculate the band gap in such dark band gap types? You see, it is for indium gallium arsenide, for gallium aluminum arsenide, it is like this. It is with these 1.424 plus 1.266x plus 0.266x squared. So if you know, if you put the value of x, you can calculate the Eg. So in this way, you can change the band gap also by varying the value of x, the amount of addition of the constituents. And for and this gallium aluminum arsenide, keep in mind, it is used in the short wavelength regions, means 0.8 to 0.9 microns, maximum 1 microns. But for longer wavelength side, if it is 1.0 to 1.6 microns, nowadays I told you, 15 used 1.55 microns. So in that case, the sources generally indium gallium arsenide phosphide, right? 1 minus x, x, y, 1 minus y. So in this case, the relations, it is like these things. Band gap can be determined using these relations, 1.35 minus 0.72y plus 0.12y square. And y and x, they are related like these things. So with this, you can calculate the band gap and you can calculate the emission wavelength for a particular materials. Okay. So with these materials and their output, etc. Now let us see the more details about these the light emitting diodes. First, the sources, the two sources we consider in details, that is LED sources and laser diode sources. First, consider the light emitting diodes. Right, it's a basically PN junctions, but we'll see It is not the conventional PN junction, it is rather heterojunctions. Why it is heterojunction? We have seen because heterojunctions will provide high power output. Right. Actually, you see what are the requirements for LEDs that we use. So all I've seen so many LEDs are there. Any indications, any instruments, if you some LEDs are there for indicating some things. But those LEDs are generally not used for public communications. Uh, LEDs that can be used for public communications, they must have these following three properties. Like it must have high radiance. That means the power, high power output, and power output. It is generally it is watts per unit solar angles per unit emitting area of the uh, surface per unit emitted per unit emitted, right. That is the high radiance. It must have high radiance. It must have fast emission response times. Well, semiconductors generally it's based on injection of current. So whenever you apply the current, immediately you will not get the light. So there'll be a delay between application of current pulse and the onset of radiations. That is called the time delay. That delay, uh, time delay should be minimum, right? So that it can have fast response times. Because 12 fiber, you will see it. It is gigabit to terabit. This range data rate will be like that. Gbps to or tbps like this range. So the response time should be very high. And third is it must have high internal quantum efficiency. I told you efficiency, it can be high internal quantum efficiency or external quantum efficiency. Internal quantum efficiency is related to the fraction of electron hole pairs that recombine radiatively. So whenever it's quite clear, when the carriers are recombined, suppose if you have a PN junctions, simple PN junctions, if you see it, right, PN junctions, P and here it is forward biased. So it is forward biased. Then you see carriers will be injected from the P side to N side, and electrons will be injected from the N side to the P side. And these carriers, when they recombine, you'll get the emission of light. But these recombinations, it can be either radiative recombinations or it can be non-radiative recombinations. So the recombinations, it can be radiative, it can be non-radiatives. Then question is non-radiative, then where the energy will go? Actually, energy can be transferred to also lattice vibration, like heat, like these things, not the radiations. So not necessarily always you'll get the emission of light, but it can be converted to some other forms, right? But the internal quantum efficiency is related to the fraction of electron hole pairs that recombine radiatively. That's why it is here. So it must have high quantum. We'll see it. How it can have high eta. And so these three things must be there for LEDs, and these can be obtained if the LEDs satisfy these two conditions. One is charge carrier confinement, and there is optical field confinement. The charge carrier confinement, this means in the junction layers where the carriers are recombined, right? More carriers should be available, right? So then more radiative recombination will be there, and that is the charge carrier confinement. More carriers should be confined in the junction layers, and in the optical field confinement, it's what is this one? Just like optical fiber, high refractive index, lower refractive index. So by here it is by varying the by varying the band gaps, you can have charge carrier confinement, and by varying the refractive indices, you can have the optical field confinement, right? So this condition must be satisfied to get the high radiance, fast response time, and high efficiency LEDs. So these conditions can be satisfied by the structure that is the heterostructures or the heterojunction. Structure contain heterojunctions. If you have the heterojunctions LEDs, then only you can have charge current confinement as well as optical field confinement. right? But again, these heterojunctions can be single heterojunctions or can be double heterojunctions. A single heterojunction means, say, one is gallium arsenide and that is gallium aluminum arsenide. One is a smaller band gap and another is higher band gap, right? But single heterojunction cannot provide these two conditions. It must have double heterojunctions, means two junctions will be there. Say one can be capital N gallium aluminum arsenide, it can be P gallium arsenide, and there can be the two junctions, and that will be P capital P gallium aluminum arsenide. Right. Interestingly, you can see it here. Generally, junctions are formed of P type and N types, but here you see one is of higher band gap and lower band gap. So you can have a junction like N capital N or P capital P. They can form also junctions because their affinity of electrons will be different, right? So by using different combinations, you can have different types of laser, different types of heterojunctions. It can be so double heterojunctions can be NPP structures, can be NPP, can be NNP, like these things. Like a lot of variations you can have it. Okay, today this much is the double heterojunctions. Next time we'll see it. Next time we'll see more about it. So till now, if you have any questions, you can ask. Today I am stopping these ones. Any questions from anybody?
No, sir.
क्या कोई क्वेश्चन नहीं है? ठीक है, then next time we'll see it.